Feamster from Georgia Tech. He'll be talking about network layer support for secure routing and access control. Nick.
Okay, thanks. So I assume I have till 2:15. Is that right? Okay. Oh, an hour. Well, those are two different things. So I'll just keep talking. Okay. So actually, I'm probably one of the least qualified speakers here because I'm not actually working in routing security so much. But I'm going to talk a bit about some network architecture things that we've been working on. Some of which pertain to routing security. In particular, one of them looks at how changes to the network address structure that may make deployment of things like SPGP easier. And then I'm going to pull a fast one on you and start talking about other sort of network layer support for security in campus and enterprise networks. Okay. So sort of a talk in multiple parts.
Some people think about those as routing security.
I do personally, but from looking at our program, it looks like routing security means BGP security. So
no, we're very welcoming.
Yeah, so that's good. I wouldn't want to kick. What's that? I wouldn't want to become a member of my own. What's that quote? I wouldn't want to be a member of a club that would have me as a member.
Thank you, Greg.
Okay, so. So this is really a talk in two parts. First, I'll talk about some network layer modifications, modifications to the address structure, and then I'll talk more about enterprise and access control problems. So the first part of the talk looks at how can we change the network layer architecture to make a lot of these different problems that people are trying to solve easier. Of course, we've seen a lot of these things in the news. Things ranging from denial of service attacks to route hijacks. We've heard a lot about already routing attacks. Spammers using the routing infrastructure to sort of conceal their identity as they mount attacks, and so forth. For each of these problems and attacks, we've been, as security researchers, we've been developing point solutions. Better spam filters, defense against DOS attacks, for routing security problems, SPGP, and so forth. And the motivation behind the first part here is to note that perhaps we shouldn't be necessarily just going after point solutions, but rather asking, is there something that's fundamentally missing from the network layer that if we could add it, solving a lot of these problems would become easier. So that's the first part of the talk. That's a modification to the network layer called AIP that I'll talk about. Then, of course, specifying security policies is actually hard as well. In particular, what we're going to look at is inside a campus and enterprise network, operators want to do things like make sure that data doesn't leave, or sensitive data doesn't leave. They also want to make sure that unauthorized users can't gain access to part or all of the resources on the network. Today, this type of policy is specified in very low-level device configuration. And what we're going to do is look at a totally new approach to doing that. Okay, so as I mentioned, this is sort of a talk in two parts. I'll first talk about AIP, or the Accountable Internet Protocol, which is, as I mentioned, an attempt to redesign the internet address structure so that accountability is more inherent to that layer. And then I'll talk in part, that actually has a number of applications, but I'll talk, since this is a secure routing workshop, I'll talk about what that has to do with SPGP in particular. And then we'll talk more about access and information flow control, figuring out how to basically design the network architecture so that those types of problems are easier to solve. And I'll talk about what we've actually built and deployed in the Georgia Tech campus network to solve these kind of problems. So again, this is sort of a talk of two minds. This first part is very, it's sort of internet-wide architecture, pretty pie in the sky, I would say. Whether or not we'll ever see something like this deployed, I think is arguable. This here is, on the other hand, very specific to a campus or enterprise network, but it's actually running. So in that sense, it's a talk in two parts as well. Okay, so let me just dive into AIP now. This is joint work with a bunch of people, including my advisor, but also Dave Anderson, Scott Schenker, and some of Scott's students. Okay. So I mentioned already that we see a plethora of problems and point solutions for each of them. The work basically starts out by asking, well, it starts out by noticing that there are sort of three different kinds of names at the IP layer. There's an address, there's a prefix, and there's an AS number. There's no actually secure binding between these. Right? So for example, there's no way to securely bind a host to its IP address, but more importantly for the secure routing problem, there's no secure binding of an AS number to IP prefixes. So this whole problem of origin authentication that we heard about becomes a very hard problem because there's no way to associate securely and accurately an IP address or an IP prefix to an owner and the AS that corresponds to that owner. So what we're going to do actually is sort of rip out IP and put something else in that makes this problem just go away entirely. Okay. So so the idea then is basically to, as I mentioned, take out IP, put something else that sort of looks like, I mean, we're still going to have internet addresses, but they're going to have a particular special structure to them, and then we're going to try to build certain things on top of them. So you can actually build a number of things. In the paper, we talk about how you can build anti-spoofing protocols. That is, test to make sure that a host isn't spoofing its IP address. But today I'm going to focus on the secure routing aspect of this. Okay, so as I mentioned, that's already so the key idea is that we're going to make these IP addresses self-certifying. So what that means is that each address is basically going to be a public key. Okay, so before we had a problem of associating a number, like an IP address or an AS number, to a public key, and now we're just going to make that problem go away because we're going to make the number, we're going to make it the key itself. Okay. So I mentioned that once we have that, it becomes a lot easier to do a lot of things that rely on sort of basic security properties. We can just build those right on top of the infrastructure that we have. So this is sort of the general motivation is that, okay, a lot of these problems are hard. Could we make them easier with a different kind of network layer address format? So here's the address format. Okay, we're going to assume the existence of still independently operated networks. We call these things ADs, or autonomous domains, and you'll see why I'm not calling them autonomous systems in just a minute. The short answer to that is because we're going to route on them. Okay, but you can sort of think of them like ASs for now, except they have some perhaps geographical locality as well. Okay, so and each host is going to have some globally unique endpoint identifier. And this is something that we actually steal from other architectural proposals, in particular the host identity protocol, or HIP, and Mike Wolfisch's earlier work on delegation-oriented architecture also uses this idea that a host is going to have a globally unique endpoint identifier. And we're going to actually make that host, or that host endpoint identifier, also a public key. Yes? Question? No? Okay. Okay. So now a host address then is going to be a concatenation of these two things. Right? It's basically going to be the AD in which, through which it can be reached, followed by the globally unique endpoint identifier. Now you may already ask, what if that host can be reached through multiple upstream ADs? No problem. We just give that host multiple addresses. You may think, isn't that a bit weird? We're giving hosts a lot of addresses. And actually, no, that's pretty common, especially with IPv6 now. We see a lot of, for example, multi-homing techniques that just involve giving the host multiple addresses. People have played that game with IPv4 as well. It's just harder to do because of the address space shortage. So that's not that weird. Okay, so then each of these components is going to be a self-certifying flat address, right? So the AD, in particular, this is the part we're going to focus on today, is just a hash of the public key of the AD. That's so it fits in a message and so that it can fit in the packet. And then self-certification basically takes care of this binding. Okay. So that's the main idea. I'm not going to talk a whole lot about EIDs today because that part of it has less to do with interdomain routing. It turns out that we can use the self-certifying nature of the EID to do things like check for address spoofing. But for the secure routing story, really, we're just going to look at the AD portion. Okay. So forwarding basically works similarly to an IPv4. The difference here being that instead of forwarding on a destination address, we're going to forward on a destination AD. Okay, so now you can kind of see why this isn't quite like an AS, because if the AS is really huge, right, chances are you may not want to forward to just anywhere in the AS. So we make these basically smaller sort of sub entities. These are like sub ASs that you sort of an atomic unit that you wouldn't mind actually routing your packets to. Okay, so packets are forwarded based on the destination AD, and then once the packet reaches its destination AD, that packet is then forwarded based on this EID, on the globally unique endpoint identifier. So the ADs that are further upstream from this destination don't need to know how to route on this part of the packet. They only need to know how to reach this destination AD. Okay, so in a sense, you can kind of think of that like routing on ASs, but instead we're routing on these sort of finer-grained AD things. You might ask, what are we getting here? Aren't you just routing on something that looks like an AS number? But remember that these are special, right? These are public keys. So what we can do is that when we distribute our routes, we can actually use BGP or SBGP as we'd like to do, right? And before, where we had this problem of how do I associate an AS number with its public key, that problem actually just goes away entirely. So I'll talk about that in some detail in the following. We don't have to use SBGP, but I will show how if that were the appropriate choice, then this problem of origin authentication that problem just goes away, and the problem of checking path signatures also becomes a heck of a lot easier. Okay, so here it is in one slide. So just quickly some definitions. I think Sharon actually covered. She definitely covered origin authentication. She probably covered path as well. But just as a refresher, right, origin says that the prefix that ASX originates actually is owned by X, and path authentication is we're concerned with the accuracy of the AS path. That is, did the sequence of ASs that this route advertisement passed through actually correspond to the ASs along the AS path? Okay, so how is this done today? So today it's not done, but how would it be done with SBGP with today's infrastructure? Well, the short answer to that is you need a PKI. You need some infrastructure that's going to map your AS number to the public key corresponding to that AS number. And of course, we know how these things work. These certificates are signed by some authority, so then you need a certificate authority. You have some delegation chain. The one that's proposed by SBGP typically follows the address allocation hierarchy. And we know that these things generally just don't work. These registries are notoriously inaccurate. It's very hard, as we discussed in the last talk, it's very hard to keep track of the rightful owner of a prefix as it gets delegated. So this mapping of prefix to owner is notoriously very hard. And on top of that, of course, you have to maintain this public key infrastructure, which adds some additional overhead. So the idea is, well, what if we could just make that problem go away? And with the architecture that I've proposed, actually it turns out you can. You just need to rip IP out and throw this new address format in. Easy, right? Okay, so but assuming you could do that, then the ADs themselves can just exchange public keys via BGP messages, and they can advertise routes just as they would with BGP. Origin authentication, notice it just becomes automatic, right? Because we're routing on a destination AD, right? So I no longer have a problem of mapping a destination prefix to the rightful owner, i.e. an origin AS, because no, we're just routing to the origin AS. We're actually routing to an origin AD, but that's it. We're done. There's no binding to even worry about.
I'm still confused by this. So can you go back one slide?
Yeah.
So the AD is the hash of the public key for that host.
The AD is the hash of the public key for this network. That's
The AD is the hash of the public key for that network, and the EID is the hash of the public key for that particular host.
that's right.
So how are those bound together by just that message?
They don't need to be bound together. These two don't need to be bound together.
So how do I know that EID belongs to that AD?
You don't, and in fact, it doesn't matter, because you're routing to the AD. Right? You don't need to know that an EID is situated in a particular AD, and in fact, that would constrain you more, right? Because that EID may be multi-homed, right? So, and if it moves, right? I mean, the binding actually it buys you nothing. What we want to do is create a binding between this and the AD and its owner and the EID and its owner. These two don't need to be. These two don't need to be coupled.
More like ASs and prefixes, and this is different.
There are no ASs and no prefixes here.
Right. So the EID just doesn't need to be originated by a particular AD.
No.
It could be originated by multiple.
Could be originated by anyone.
And
It
how
doesn't.
does the EID tell the world that he wants to be originated by this particular AD and not someone who's trying to hijack him?
So back to here. So you're saying, like, how do I know that this is legitimate?
He's agreed to be attached to AD1, for instance. How do I know that EID has agreed to be attached to AD1? Because that's really the origin authentication problem, right? At least in your framework, which is different. But
Well, no, because actually, so this basically names the host, right? This basically says I want to be so for example, see how this would work in DNS, right? So I look up the host and I get this back. So the host would basically put that, or whoever manages that lookup would put that binding in place, right? So when I look up the name for the host, I get back this. I might actually get back 82:EID. I might get back 83:EID. So I get a list of those, right?
So what happens?
Doesn't matter, right? As long as I can route to 81, and as long as that address is correct, then
then
I'm fine.
So let me rephrase the question.
Okay.
Suppose that 81 and 83 are legitimately connected to this EID, and 82 is an attacker. Okay, and he wants to claim to the world that he's connected to the EID, so he just does that. He says 82:EID.
So no one's going to answer to that, right?
Why not?
Okay, so that's where spoofing would come in. So I wasn't planning to talk about that, but no one can claim that they have EID, right? So let's suppose that 82 wanted to do that. So you're eventually going to start trying to communicate with 82:EID.
Yeah.
Not going to work out, right? Because whoever's spoofing that address doesn't have the private key corresponding to the public key of EID. So, I mean, you're going to be able to tell that that's not actually a legitimate endpoint.
My impression is that you're saying that 82:EID is really a different address, and no one would actually try to talk to that anyway.
Yep. Well, there's that.
Because of application layer stuff, not because of this key.
Yeah.
But I guess I'm now missing something because I thought if you were only routing to the AD, then if you saw, let's say that 82:EID was inserted into this thing where I wanted to look up the name for something and
Right.
somehow I got back.
All I know when I get that.
I'm trying to route to 82 though, right?
So all I know is that the routing infrastructure is going to take me to 82.
But
That could be
bad,
That
right?
could be like a traffic attraction.
Doesn't matter, right? I mean, so I get there, right? Then I care that I want to talk to EID. It's going to be very easy to tell that I'm not talking to EID.
But
at
isn't that the
point.
same as a prefix hijack?
Yeah, it's identical to that's
No
the
way.
thing.
No,
You don't
no,
actually
totally not. I mean,
know like,
I mean,
you don't actually. Let's say
there's
you're not
there's no way that
connected to
82 is going to be able to masquerade as EID.
But he can,
That's-
for example, drop all the traffic for EID. So for instance, suppose 82
But-
is a better path. So let's just talk in the framework of my talk, okay? Just because we're getting a disconnect here, so I want to understand.
Well,
So 82 is the red attacker in my talk, and he's getting all the traffic, and he refuses to deliver it. To
I'm gonna be able to detect that very quickly, right? Because 82 the 82 colon EID like would not be. There's no one in 82 that could sign for EID. Yeah.
If the path you're saying there is correct, then I think you need to be talking more. What I'm hearing you say though is that the total address is 82 colon EID,
That's correct.
and
So maybe you should talk about the
and no one would
anti-spoofing
key to
network.
it anyway.
How do they know? Why wouldn't they just send it there? It's a nice address, I'm sending it there. Why
It's
should-
random. You picked it out of the ether.
Yeah, I mean, if I see that, I know it's going to go to 82. What's the problem? That
Well,
is the address,
the,
right?
the problem is that
There
you-
is no one, but there is no one with EID in 82.
Yes,
So-
but 82 gets the traffic.
Yeah, 82.
So what? I mean, what's the problem at that point? I mean, I can very easily then test that there's no endpoint then.
Well, I'm going to call the AS number, the AD whatever,
Right.
is the first part of the address. It's almost as though we're adding some octets in front of an IP address that are the AS number. Is
That's
that what you're
accurate.
thinking?
Yeah, that's except that it's not an AS number. It's a key. But yes,
The AD
that's-
is a key as well?
the AD is a key as well.
Okay.
So it's a routing problem rather than
So the application would be trying to query 81 colon EID, it would never query 82 colon EID. That's what you're saying, like whatever's routing through this network would never.
If I want to route to 82 colon EID, I can. Right? I know that my traffic's going to go to 82. But maybe I don't want to talk to 82 colon EID. I
So
probably
this-
want to talk to 81 colon EID, right?
So what it's saying is that
Yeah.
your network address is forever bound to your AD, your AS number, your upstream.
Yep. And you can have multiple.
And so there is no concept of address portability here.
There is no address portability. Yeah. But the way we solve that is by giving each host multiple addresses. Right?
What prevents a false address from being assigned to a host at some point?
What's the scenario that you have in mind here? So someone just mints an EID and then creates a new address? You can't defend against that.
So here's the scenario. So you have some website, like CNN.com, and it has multiple ADs that it's connected to.
Mm-hmm.
And then there's some other malicious AD that wants to claim that CNN.com is also connected to it. Okay? Which is the EID. So now, if the world, when it wants to reach CNN.com, just says, give me CNN.com connected to any AD, some of that world will end up going to the attacker. But in your
You would have to control DNS to do that as well, right?
right, so what you're
Okay,
assuming is that,
so we assume a secure naming infrastructure,
right.
but so does SPGP,
Sure,
right?
sure.
So basically, we've removed like one element from the equation here.
Right, so the bottom line is when someone would go to CNN.com, it would query this whatever it is, and it would never get that malicious AD, colon EID, because that would not be in whatever the security
Correct.
infrastructure is.
Correct.
It
Yeah,
would
we
never
ass-
be allowed to
correct.
enter into the
Yeah,
network.
correct. Yeah. Yeah. So we do assume like secure naming, but that's no different than SPGP, right? I mean, in SPGP you could have perfectly secure routing advertisements.
Yeah.
If I get a bogus IP address returned as an A record, I'm still screwed, right? So
this is easier to implement because you don't need PKI to actually implement it, right?
yes, this
Anybody
is
who has the EID can
yes.
make a signature saying
Yeah.
yes at this.
Yeah. So yeah, exactly. So this does not give you anything as far as naming. It still has all the problems that DNS has, but it basically takes away some of the PKI issues with SPGP. Okay. So actually, are there any other questions. Did I convince you at least that that we've got that part of the problem solved? Okay. I can see there are certainly other issues. In particular, so this is what we just talked about. Traffic engineering becomes more difficult, actually, because before, with prefixes, we rely on the ability to chop things up into smaller chunks, right, and route them in different ways. Here, you actually just have an atomic unit. You can't take your public key and chop it in half and route half the traffic one way and half the traffic the other way. So we do lose some things as far as the granularity on which you may be able to forward. Actually, one thing I didn't mention was the address portability. So there's a trade-off, right? Your host has that AD binding. So if it wants to change upstreams, it's got to have a new address as well. If it wants to use multiple upstreams, it has to have multiple addresses. If keys are compromised, that's a similar problem, right? I mean, we basically need to generate a new address. I don't think actually some of these things are that big of a deal, though. I already mentioned why I thought having multiple addresses was probably fine. Key compromise as well. If you're basically relying on naming to feed you your AD-EID pairs anyway, then yes, you may be vulnerable for the time at which that compromised IP still lives in someone's cache. But again, that's probably, I view that as a similar level of vulnerability to other things that we've seen, cache poisoning and such. Okay, so, and then the other is, of course, that it's completely flat, right? So there's no way to aggregate addresses here. So if we're talking about, that may be fine, because whereas now we're routing on IP prefixes, and there are like 300,000 of them. Here, and of course there are many, many more hosts. Here we're routing on ADs, and our thinking is, well, there are going to be less of those. It's hard to say exactly how many, though. There are going to be more than at least the number of ASs, right? Because we're mapping ADs from ASs. But if we want to do things like traffic engineering, or we want to have more fine-grained control over where the traffic actually goes to its destination, we're going to have to chop the AS into smaller pieces. So a perhaps less conservative calculation would be AS cross POP, which is still, maybe in the order of, hundreds of thousands to maybe a million, maybe a couple million. But that may still be feasible. The other concern is the length of the AS path. So as we know, and didn't bring the graph, but as we know, the AS paths are getting shorter. That does not mean that the AD paths are getting shorter. Why we care? The length of the AD path basically affects how many signatures we have to check, right? So with SPGP, of course, you've got to check one per AS along the path. Here you've got to check one per AD along the path. So if our AD paths are getting very long, that's more signatures.
What about the analog to OSPF for routing within a location or a company?
Could you basically use this for OSPF?
No, right now I've got hierarchy not just at the BGP level, but at my IGP level as well.
Right.
And if my host addresses are flat addresses, I don't have that anymore.
Oh, okay. So you're talking about like if an ISP is using OSPF areas and you have hierarchical addresses within.
Never mind even areas.
To selectively choose your keys so that the upper 8 bits of the hash turned into your internal addresses. Selectively choose your internal address keys. Blah.
Generation is expensive. They have to try order 256 tries to get a key in the right land.
That's order small.
Until my iPhone wanders from one land to the next and has to put go on, yeah. Mobility is another interesting question, we won't go into now.
Yeah, of course, if it's flat, then you're okay. But yeah, if you do the proposal that was suggested,
This
then
machine has a new IP address that it didn't have yesterday.
yeah. I mean, one might argue that within an AD, it doesn't make sense to renumber a host anyway. I mean, I think I would make that argument. And I mean, even on very large campus networks, we get away with that just fine, right? I mean, they run very large VLAN for a wireless network of 10,000 hosts. Yeah, you do run into scaling problems eventually, but okay, maybe we keep our IDs below that size. Yeah.
I was trying to understand, I think it's interesting, I'm just trying to understand what the constraints are and limits are, and I understand it better now.
Yeah, you're very right to point out that we do need this flat forwarding inside an AD. Okay. So unless there are more comments there, I want to talk about the other piece of this talk, which is sort of less crazy but more limited.
Actually, before you go
Yeah.
on,
Yes.
back to the, what are you calling this, AIP?
AIP. Yes.
What are your ideas for incremental deployability? How do you roll this out on the net?
That's a good question. You could you could, for example, have I don't know. Maybe you could have some kind of islands from which you tunnel between. It seems like you could do something of that nature. Like, for example, you could have smaller areas where you've managed to deploy this. Certainly, the EID part is totally deployable.
Say I run a big content distribution network. Say I'm Yahoo.
Okay.
I want to tell people to reach me. I can tell them to reach me on IPv4. I do that now. I can tell them to reach me on IPv6.
Mm-hmm.
That's likely to break things. I don't want to do that now. I can tell them to reach me on this. I really don't want to do this because no one will reach me, and I'll lose traffic and eyeballs and revenue.
Mm-hmm. Actually, now, I mean, correct me if I'm wrong. Like, I mean, these CDNs will return v6 addresses as well. I mean, the quad A's are coming back, right? So if you support v6, you could choose to route that way. So could you do an incremental deployment like that this way?
As poorly as we've done the v6 deployment?
Define poor. Well, there's a question of is it deployed versus does it work, right? I mean, sure, the deployment is limited, but I mean, technically speaking, there's nothing wrong with dual stack or deployment, right? I mean, it works.
Mm-hmm.
It's just there's no incentive to actually use it. So maybe you could make the same argument here, right?
Well, unless it's, for example, a company that wants to make sure that all its employees, or make sure that only its employees can access it, and so it forces all its employees to run AIP, and the enterprise itself also runs AIP internally.
Yeah.
Now, if you had say a content provider who couldn't get enough address space, one of your advantages here is you get free address space. You're using up other people's routing table entries, but you're getting free address space. And
It's the v6 approach, right?
To quote Fred Brooks, the only time you get something for nothing is when you previously got nothing for something, and I think that's what you're talking about.
Exactly. So we're putting the RIRs out of business. So that's fine. That's in fact great. But what am I going to publish on this new V8 that people are willing to upgrade their host stacks and tell their ISPs to upgrade so that they can reach?
Maybe it's something like Jad suggested, like, I mean, he mentioned the case of enterprise networks, but maybe it's, okay, I'm a banking site or a financial site, and sure, I'll advertise v4, v6, and AIP, depending on how paranoid you are. You know, maybe try to reach me through the AIP infrastructure, right? So, some people who perhaps really care about the security of their routes might be willing to make that switch. And it wouldn't take that many ASs to deploy it in that kind of context, right? Because, I mean, AS paths between the types of content like that people may care about and the eyeballs actually aren't that long, right? So you could probably even imagine doing it between pairs of ASs. Right? Maybe a bank deploys it, and then maybe Comcast deploys it and says, hey, we've got this special service, like, we'll secure your routes to your financial institution or something, right? And you just need one peering. So, I don't know, does that?
Or a big enterprise like Google that has a lot of flex tells, look, I want all my ASs to have something like this, and then it will only share with the ASs who do, for example.
Right. I have a hard time imagining Google turning it off for AIP,
Yeah,
but
not Google, but
yeah.
some, maybe
But yeah,
NSA,
someone-
maybe the NSA.
Yeah.
for example.
yeah, someone like NSA, that seems like a reasonable. In order to peer with us, you must implement this. Yeah. Unclear why people haven't used that lever with SVGP actually. But, yeah. Okay, good. So, no other questions or flames? Okay, so I wanted to take the rest of the time, which is, I don't know how much time that is, 20 minutes, okay, to talk about some things we've actually built and deployed on the Georgia Tech campus. These relate to access control and information flow control in the campus network. So here, I guess, VJ would hopefully save me and say, yeah, this is still secure routing, but it's not secure BGP anymore. So the main problem here that we're looking at is how to enforce high-level security policies with in ways that are easier to manage, check, and enforce. Today, this is done with low-level router mechanisms and various on-path devices like firewalls. So it's a mishmash of access control lists, firewalls, and VLANs. I'll get into some details of how it's done actually today. But by the end of the talk, hopefully I will have convinced you that this bag of tricks is just the wrong way to be thinking about things. It's hard to get these policies right, not even getting into some of the fundamental problems with VLANs, like there are a limited number of them. If we just talk about how hard it is to configure the network, it's difficult to do this because the device configurations are at a fairly low level, and also you have to coordinate across devices. In particular, even just looking at VLANs, you have problems with sort of a global VLAN ID space, but also looking at access control lists and other aspects to this, ensuring that the policies are consistent across the routers and you haven't unintentionally created a partition, or worse, unintentionally created a sort of transitive connectivity between two parts of the network that you want it to be partitioned. Actually turns out to be hard to reason about. I'm not going to talk about that today. There's actually a lot of previous work by I think Jeff Shee and some others on various problems that can arise when you configure access control at the device level. So our approach here is actually to, we're going to sort of pose a question. Can you actually centralize the policy? So let's have network devices, instead of implementing access control lists and firewall rules and VLANs, let's have them just have the most minimal possible configuration, maybe enough to bootstrap the connectivity, and then let's do everything else in terms of a centralized policy specification, implemented at some kind of centralized controller that we can then, where we can check the policy that we've specified and also control the behavior of the switches directly through forwarding behavior rather than indirectly through how each device is configured and their interactions. I should say that we're not done with this. We're moving towards like bigger questions like what should that policy specification language look like? But what I'm going to show you today is sort of like a proof of concept of something we built for like one example policy. Okay, so one challenge that I didn't list was what the heck should this policy language be? And that one I'm not going to really answer. But these others, we've started to figure out a little bit more, like what is the performance hit you take by centralizing policy and requiring forwarding logic to be pushed back into switches rather than having everything sit on the switch. Okay, so I'll probably just talk about the first one, this access control problem. Yeah.
Maybe you'll explain this later, but when you say pushing forwarding onto the switches, does that mean you sort of, every packet that the switch has to route, it has to ask the central device what to do and then it goes?
No, you can actually push rules. So if you're familiar with OpenFlow or the Knox controller, so basically the idea is that the switch will have rules that are basically TCAM entries that match on fields of the flow, right? And then the logic comes in, what should those entries be? So the smarts basically live somewhere else, not on the switch, but once those rules are in the switch, all the forwarding can happen right there at the switch. Does that make sense?
So how would the rules change? Like what might be a scenario? So by
I'm going to come to that actually, yeah. So let's look at this access control problem, because there's actually an example where the rules are changing. And that's actually where you do pay some overhead. You basically pay some performance, because some packets do actually have to come somewhere else besides the switch before those rules are installed. But that isn't steady state. Okay, so first let's look at sort of how this is done. What I'm going to do is explain how this is done today. The problem that we're trying to solve is actually access control. The first problem we're trying to solve is, can we do just what the campus network operators do today, but in a much better way? So right now, I'll talk about some details of how they do this. They do it using VLANs and sort of DHCP-based reassignment of hosts when a host successfully authenticates. There are a bunch of problems with that, but one of the bigger ones is that it's actually very hard to remap a host from one VLAN to another. When they do it, the only way that you can be sure that this is going to work out for the host, when the host successfully authenticates, is to reboot the host, and it basically re-DHCPs and gets a new IP, gets put on the new subnet and the new VLAN. Now, suppose a host is compromised and you want to throw it back into a garden wall or quarantine it. Now you have a hard time actually moving it from one VLAN to another, because you can't guarantee what the host is actually doing. Another problem is that okay, so that's sort of like the static nature of it. It's very hard to move stuff around. The other is that it's very coarse-grained, right? So there are a limited number of VLANs. There are it's 12 bits, right? So there are about 4,000 VLAN IDs. Sounds like a lot of VLANs, but very quickly these things get depleted. So if you think about a campus network with tens of thousands of people, hundreds of departments, right? So now you're already down to like tens of VLANs per department. Now you're talking about research groups or other administrative entities. You're already out. But wait, actually lots of firewalls actually require a dedicated VLAN. Further, some of those firewalls are virtual, so you need a VLAN ID like for one side of the firewall and another one for the other side. So very quickly you run out of VLANs. So that limits your ability to sort of chop up the network by virtual LANs. In particular, you're not going to do anything of the nature of, Steve is visiting campus. Let's give him a special, let's write a special policy for him so that he can use the web and SSH and whatever other protocols he wants to. But a normal guest, basically doesn't get any of those special privileges that they just get port 80. So the current way of going about it is coarse-grained, in particular, as one example for access control. But another example is, suppose you see a host that's compromised. You'd like to perhaps do something to that host. Well, what? And now the question is, well, it depends. Is it a guest? In that case, maybe we want to drop it. Is it a faculty member? Maybe you don't want to drop it. Maybe you want to redirect them or to a patch site or something. Is it the dean or the president? Well, maybe you want to send a personal envoy to go fix it, right? So you may want to take different kinds of actions for the same incident, and you may want to actually code that into your policy somehow, rather than just relying on either sort of one coarse hammer or nothing. The other is, supposing you wanted to say quarantine, right? Well, what you'd like to do is take one infected host and throw it in its own sandbox, right? But actually you can't do that. You don't have enough VLANs, right? So what they do today is throw all the hosts that are infected with anything into one VLAN. So like the sick VLAN where everyone can infect each other. These are a number of the problems that arise with today's approach, and the alternative that we come up with is to basically say, well, let's not do any of that. Let's not rely on VLANs. Let's not rely on any kind of on-path device. Let's just do forwarding. Let's sort of bootstrap our forwarding, and then let's use some central controller to keep track of what's going on with each host. And as we see events from those hosts, for example, a host is successfully authenticated, and it's Steve, or host is successfully authenticated and it's Aaron. Right? We may do one thing or another depending on who it is and what event we just saw. Okay, so that's basically the approach. So actually, I'm running a little low on time, but I think we have enough time to sort of go through some details here. So this is basically how this works today. I'll just put up the full thing. So host comes on, the switch sees a new MAC address, and it uses VLAN query protocol and a VMPS to basically be assigned to the private VLAN with a private IP. So right now, it's an unauthenticated host sitting somewhere in the, not on the public network. At this point, this host is redirected to some web authentication portal. This portal, if the authentication succeeds, is going to basically tell VMPS to map this MAC address that belongs to this host to a new VLAN, i.e. the public VLAN. And then also, we're going to need that host to get a public IP address that corresponds to that public VLAN, so that host is actually going to need to reboot. That's really the only way that the operator knows how to guarantee that it's really gotten a new IP address. Of course, there are other ways to do it, but for keeping trouble tickets out of the operator's hands, that's basically what they ask the host to do. Okay, so that's basically the way things work today, and I've already sort of mentioned various problems with this. Yeah.
Can you just explain why you need this private IP and then you get the public IP? So is it so that you can go through web authentication?
It's a security issue. So like when a new host arrives, you certainly don't want it. So suppose it's infected, right? You certainly don't want to just plug it in and have it basically talk to everyone else on your network. So what they do is they basically throw it off into some safe quarantine for a while until they say, okay, we know who this is, and actually they also scan it to see like, okay, are there any known vulnerabilities that we can detect remotely from this host? So until they've ascertained that this is someone that we want to have on the network and this is an okay host, they leave it off on a separate VLAN. That effectively partitions it from the other hosts on the network.
Okay, and when you say web authentication, that's some kind of scanning and verifying that this thing is allowed to be here?
Well, so you would basically log in you would say, I'm Sharon, here are my authentication credentials. And this thing would basically determine like, okay, this is a guest, or this is a student, or this is a faculty member, and this is okay, right? So let's throw them on the, it's okay now, they can use the campus VLAN or whatever VLAN they should be assigned to. Okay, so I mentioned this stuff. Okay, so here is an alternate approach which gets rid of a lot of these on-path access control and firewall boxes. It also gets rid of the need to use VLANs for this problem, and it also allows us to dynamically take one host and place it in one part of the network or the other, the quarantine or the public part of the network.
When you say control forwarding stage, is that anything more conceptually than changing the ACL, having large ACLs?
That is, it's similar actually, yeah. So actually, that's actually a really good point, and I'm glad you brought it up because the implementation choice we've used is the OpenFlow switch API, but actually you could presumably do it if you had like a remote. So if you had a remote controller of ACLs, you could do it that way as well. We haven't done it that way, but I think there's nothing preventing you from implementing it that way. Yeah, very good question. Okay, so Now each state has some, or each host has some state. One part that we haven't implemented, but this is something we're working on now in conjunction with the policy, is to associate each host with some security class. So right now we basically just assume, okay, it's just a host, but let's put it in a unregistered state or authenticated state or a infected state and do something according to that. But the example I mentioned before with, hey, you may want to take different actions depending on whether this is a guest or a student or a faculty member, that basically requires us to expand our policy specification in a certain way that we haven't done yet. We're looking at things like the lattice security model for doing this, but we haven't implemented that. Okay.
Can't that be just translated into more states?
I think so, and this is actually some theory that I'm trying to get to the bottom of. So you could, for example, say this is just one giant state machine, but I don't understand yet if that exposes us to some other risks, because you certainly don't want a student to ever become a faculty. Well, maybe in some cases you do, but not in the case of host authentication, right? So, right, I don't know. Actually, if you have suggestions on this, I'd be curious to talk to you more about it, because right now we're thinking like maybe we just have a separate state machine for each host, or for each class, and we assume that a user or a principal of one type can't become a.
I mean, what you just suggested is just basically making the security class the first state that any host gets to, right?
Yep.
And so there's one state which is security class not yet decided on, and then security class decided on, and everything else.
You could basically fan out from there.
Yeah.
Now, as long as you had no transition edges between, like, so you have sort of a fan out,
exactly.
then I think they might be equivalent.
Yeah,
Like,
no, that's fine.
yeah, I think they might be equivalent at that point. Yeah. Yeah. So you could probably represent it as one state machine if you did it that way. I don't know if we'll actually do it. So yeah, I'm not quite sure. Conceptually, to me, they seem equivalent, but I'm not sure if there's some detail in the theory I just don't understand yet. Okay, so I think we get the basic idea. So this is now actually what happens, and this is an example. So this is something that we've implemented, and this is actually what's running in our department now. But you could imagine perhaps specifying other state machines. But this is basically what we're doing right now. So the idea basically is that a host shows up with a new MAC address, and now this state machine is something that a central controller is keeping track of per host. And so and this is actually your question, right? Now the MAC address, the host arrives, the switch sees a new MAC address. At this point, it doesn't know what to do, so actually sends that packet to the controller. So at that point, you do have a packet going to the controller. So now the controller is now keeping track of this the state of this host. When it receives a message from something, note, we don't care what. It could be that web portal. In fact, we're using a web portal, but it could be, some kind of, other authentication. We don't care. We just are waiting for a message to say, yes, this MAC address has successfully authenticated itself. Then the controller moves that host into this other state. Now, corresponding to each of these states are forwarding table entries in the switch. I think I have an example of that later, but let's see. So, for example, here, just in case I don't, here you have rules in your switch that basically say, well, you can get to the web portal or whatever via port 80. You can do DHCP, you can do DNS, perhaps on the local network. You can do ARP, but anything else is blocked, right? Okay. Okay. So the authentication fails. Basically, you're gonna not change those rules. If you're going to, okay. So basically, what happens here is the host is authenticated, and now the scanning process occurs, right? We basically just want to check that this host is clean. Right, so now perhaps we open up some additional ports in our switch to allow that scan to take place. At that point, if the scan passes, then we default to whatever set of flow table rules, or forwarding table rules, I should say, correspond to the security level of that host. Okay, so then, of course, if a vulnerability is detected, we want to basically update our forwarding table entries and move that host back into some state where we either scan it or quarantine it. Okay, so I think I just went through that. Let me skip this. Okay. So this comes to Steve's question a little bit, like how do we do this? And I think the point is well taken. We could do this actually in a number of ways. For example, with ACLs, we could even do it with expect and reconfiguring the routers. There's no particular, we're not conceptually bound to our implementation choice here. This was basically a matter of convenience, i.e. We have some switches that support it. It's a fairly clean interface. There's pretty good support for the OpenFlow controllers, and once we have the ability to directly touch the forwarding table entries, that is a little bit more direct than, say, touching configurations. There's some usability and convenience considerations that went into our particular choice of this. What it is, for those of you who don't know, this is basically allows an off-box controller to affect the forwarding table entries in the switch. These forwarding table entries are, as I mentioned already, they're CAM entries, right? So what the switch can then do is match packets from a flow on a particular subset of the fields. Jad can correct me if I'm wrong, but I think there are 11, something like, maybe there are more now in the later versions.
I think it's 13.
Okay, it's 13. So based on whether or not these fields match or not, we can take one of a number of actions, including drop the packet, forward it to a controller, forward it out a particular output port, or take the default operation.
Actually,
There
you
may
can do
be-
multiple actions.
Okay,
So you can do multiple actions at the same time. And in addition to the actions that you mentioned, you can also put the packet on a particular queue on the switch.
oh nice, okay. Is
Well,
that the s-
also later, as things develop and as more switches allow you, you can also change or rewrite the MAC address of the packet as it's going through, or the IP to
I see.
NAV and so on.
So that'll be handy. So you mentioned putting it on a queue. So that's going to be actually really important for this as well, because another thing that we're looking at, in addition to access control, is QoS. Right, so you could imagine then, okay, put the guest packets on the slow queue, and
Yeah.
so the actions that I showed you on that state machine before were pretty rudimentary. It's like, okay, you're in the operation state, like go wild, send whatever. But depending on who you are, you might actually be in the rate limited state or the
Yeah, so I'm not sure
the
whether ACLs
full
will
throttle
actually
state.
allow you to do things like that.
I think with everything that we've done so far, you could probably do it with ACLs, but it sounds like, and some of these capabilities I think are like, they're just coming about, right? I mean,
Yeah.
so as these new capabilities come about, hopefully we'll be able to like leverage this to do even more than what you could do today with, say the ACL-based approach. Okay, so yes, it's real. This is basically our deployment of this. We're basically down here. The network where we've implemented this is in 2 labs in the Georgia Tech College of Computing. This one is called the they're actually both part of this research NOC, which is sort of a joint venture between the computer science department and OIT. So we have people in OIT who, as I mentioned, were the genesis of this problem. They said, hey, our access control framework really stinks because of all these things that I mentioned. Can you help us fix it? And we said, hey, well, we think we can. So they basically have given us this playground and a number of switches in the CS building, and I should say a place to deploy a number of switches in the CS building, a couple other buildings on campus where we've actually deployed this. So then this is then connected out to the rest of the internet. Okay, so some challenges some of which have already come up, some of which I don't know yet how to answer. But these are the kinds of things that we are studying in the current deployment. One is sort of how many forwarding table entries are we going to need? So I mentioned already, hey, with this other approach, we're going to run out of VLAN IDs. Well, here we have a different problem, which is can the switch actually hold all these forwarding table entries for the amount of traffic load that we need to support, right? Because you can imagine very quickly as new hosts, as new hosts arrive. So, for example, the wireless network has nearly 10,000 concurrent users. Probably we're not going to rely on one switch to do this kind of access control. So we're going to need to somehow figure out either how to wait that out or to design things better so that we can balance our load better between the controller and the switches, or somehow distribute the access control better. We have done some initial measurements just to see, like, okay, in terms of, we just take basically a 100 millisecond RTT path and we just throw this access control framework on it. So we're basically paying like a 20% hit right now. This is actually going through a software switch, and this is after the initial setup, right? So this is after the authentication and all that traffic to the controller takes place. So we're still seeing some performance overhead as far as round trip, but again, as I mentioned, this is all in software. So hopefully, as our implementation matures, we'll see that go down. Okay, so let's see. Okay, so that's actually it. I'm not going to talk about the third part, which was another thing that we're doing in conjunction with this is information flow control. That is, how do you basically control who can pass information from one part of the network to the other. There's no time for that, so instead, what I want to spend the last minus 2 minutes on is next steps here. So I think one of the things I hope that I've convinced you at least that this alternate way of doing things is interesting and holds some promise. Rather than configuring policy at low level and at a device level, this basically gives us the opportunity to configure things configure access control at a network level, sort of at a network-wide level. That presents a lot of opportunities, modulo some of these challenges. One of them I think that we haven't figured out, but if we could, I think it would be really exciting is this gives you the opportunity to configure the network from one place. Well, now that means that you could do something like presumably what Boone will talk about later this afternoon, right? Could you basically have a declarative specification for what you want to have happen across your network, right? Could you say, I want these groups of people to be able to talk to one another, and I want this to happen when Steve comes, and this to happen when Boone comes, and then that's it. Like, no more device configuration. I just plug everything in. So I think we're still quite a ways away from that, but I think we're one step closer with this because we are now to the point where we can have a network-wide policy specification in one place. Yeah. Thanks.
So we probably have time for half a question.
I have a question. Please go back to the previous slide where you had the delay graph.
Yeah.
Is that just a delay on your initial authentication of the farm?
Yeah, sorry, I
Is that a
misspoke.
delay on every
I
packet?
misspoke. Yeah, I said that it was the delay on every packet, but it's the delay on the authentication.
Okay.
Yeah, sorry, I
So
misspoke.
once you approve this path,
Then
we'll
we
back
should
to
be
my
fine.
normal
Yeah.
performance.
Yes.
Okay.
So we have some time for a short 3 to 5 minute break. And if you have questions for Nick, you can take some of that time also to chat with him.
Yeah.